Hello students. In the last video we talked about the row column method, and we saw if we have two arbitrary matrices we get something like this. And you'll notice that I could actually rewrite this C here. I could write it as a sum of matrices, AF, CF, plus BG, BH, DG, DH. All I'm doing is I'm splitting up the pieces, first piece, second piece, first piece, second piece. I'm putting all the first pieces into one matrix. I'm putting all the second pieces into another matrix. So hopefully you can all see what I did. This is also equal to AB. So let's try to figure out what's going on here. I'm sort of noticing something. I'm noticing that I have some E's in common here and some F's in common here. But I'm also noticing that I have some A's in common here and C's in common here. And similarly, G's and H's and B's and D's over here. So this is actually suggesting that there might be another way to look at this. So that's what I'd like to try next, is a new idea. And instead of row column, what I'd like to consider is maybe the opposite, something with columns and rows. So here's what I'd like to consider. I'd like to consider what would happen. Well, let's rewrite this. E, F, G, H. Okay? If I try to take some sort of a column times row multiplication. So what if I took the first column times the first row here? I'd get AC times EF. So if I compute this, AC times EF, what's this equal to? Well, that would be AE, just using my existing knowledge of matrix multiplication, right? Row, column, these are short because I'll have 1 times 1 in each of these spots. 1 entry times 1 entry, and 1 entry times 1 entry. And I want you to notice something, if I can find the piece of paper I just moved, which I did. Congratulations to me. Does this look familiar? Absolutely. It looks familiar. This is exactly the first matrix. So the first matrix, when I broke this apart, well, that's exactly what I get if I take the first row times the first column. I mean, the first column times the first row, instead of the first row times the first column and doing all the different row-column combinations. Okay. Can anyone think of a way that I might get the second matrix if I got this first matrix from multiplying the first column times the first row? Well, you probably have already guessed it. Let's try taking the second column, BD, times GH. And what do I get? Well, I'm going to get BG, BH, DG, DH. So these are very easy to find, right? I'm just taking, for the entry in row I, column J, I'm just taking the ith entry of the first vector and the jth entry of the second. And I can't even accidentally get the wrong value, right? Because there's not more than one row to look at in this matrix. There's not more than one column to look at. So this might be even a more sort of idiot proof. I can't accidentally scan the wrong point doing this. So what I could write is okay, this is equal to the first row, the first column times the first row plus the second column times the second row. And this is another perfectly good way of multiplying matrices. So let's try it with an example. Let's do the same example we did before, which looks like it was 2, 1, 0, minus 1, 0, 1, minus 2, 3. So in order to do this, what I'm going to take is I'm going to take column, row, 2, 0, 0, 1, plus column, second row. Now, of course, I wouldn't necessarily need to write this out if I got good at doing it in this fashion. I could just sort of get this from looking at this column in this row, and then looking at this column in that row. But for a first example, I definitely should write this out, especially for a lesson. So I've written this out. What do I get here? Well, let's see. I'm going to get 2 times 0, 2 times 1, 0 times 0, and 0 times 1. And here I get 1 times minus 2, 1 times 3, minus 1 times minus 2, and minus 1 times 3. And I put these together, and what do I get? I get minus 2, 5, 2, and minus 3. This really takes the same amount of steps when you think about it. We're going to have just as many multiplies and just as many sums. However, well, first of all, let me show you that it matches. Otherwise, you might not even consider doing it this way. And it does match in general. I mean, it comes, the proof of it is that exact thing where we split it up. We take the original definition of matrix multiplication and we just split it up into 2 pieces or 3 pieces or 4 pieces depending on the size of our matrix. It doesn't change. There are some proofs which are more easily done using this method of matrix multiplication. Some proofs involving matrix multiplication go through quickly with this method that they do not go through as quickly with the other. So this is a good trick to have in your tool belt. It's a matter of preference, but it's handy to know more than one way of how to do things. Okay, so now I'm going to call this, there's a nice name for it, obviously, sort of, the column row method of matrix multiplication. And it's not the only method that we have. These are not the only 2 methods. Let's talk about another way of doing it. Let's save that for the next video.